Some comets tumble, others flare, but 3I-ATLAS did something no comet should ever do. It hit the brakes on its way to the Sun, then changed its mind and started accelerating. Before you click off and think it's rubbish, hear this. We have new images that confirm the phenomenon. Let me explain. First, it vented gas toward the Sun, like it was fighting gravity itself. Then, weeks later, it flipped, firing its jets the other way, like a spacecraft waking from silence. Astronomers call it a jet inversion. Avi Loeb calls it something worth losing sleep over. And tonight, so will we. Because if this was a controlled manoeuvre near perihelion, then someone, or something, just used the Sun as a slingshot. Stay until the end, to understand what 3I-ATLAS might be trying to tell us about itself and about us. If these mysteries have you on edge the way they have me, don't just watch, join the hunt. Hit like and subscribe so you don't miss a single revelation as this story unfolds, moment by moment in real time. Tell me in the comments where you're watching from, what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep this signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. Part 1. Breaking news. What you're looking at is something no comet has done before. On your screen right now, two images sit side by side. The first, captured by the Hubble Space Telescope on July 21, 2025, shows a comet glowing with an unusual brightness pointing directly toward the Sun. The second image, taken weeks later by the Nordic Optical Telescope, shows the same object, but now its tail streams away from the Sun like every well-behaved comet should. Between these two moments, something changed. Something that shouldn't be possible happened to interstellar object 3I-ATLAS. The claim sounds simple enough to make you dismiss it. Comets change all the time, right? They develop tails, they brighten, they fragment. We've watched them do their cosmic dance for centuries. But this is different. This object appears to have reversed its jet orientation entirely. In July, it was emitting material toward the Sun, creating what astronomers call an anti-tail, a sun-facing glow that defied the usual physics of solar radiation pressure. Then, as summer turned to fall, observers watched that forward-facing emission fade while a new tail grew in the opposite direction, streaming away from our star exactly as textbook physics predicts. You might be thinking this is just a viewing angle trick, some optical illusion created by Earth's changing position relative to the comet's trajectory. We see these perspective effects all the time in astronomy. A galaxy that looks edge-on from one angle appears face-on from another. It's all about where you're standing in the cosmic theatre. But the scientists tracking 3I-ATLAS have ruled out the simple explanations. The timing is wrong for a pure geometry effect. The composition of the material being shed changed between the two periods. The morphology, that technical term for the shape and structure of the tail, evolved in ways that suggest something intrinsic flipped inside this object. The Nordic Optical Telescope tracked this transformation through July, August and September. Frame by frame, image by image, they documented the sun-facing jet growing fainter, while the anti-solar tail strengthened and lengthened. This wasn't a sudden switch like flipping a light. It was a gradual transition, a slow reversal that played out over weeks as the comet continued its hyperbolic plunge toward the inner solar system. And that gradual nature is precisely what makes this so troubling for conventional explanations. Here's where we need to understand what we're actually seeing. When material jets off a comet, it carries momentum. It pushes. If you're shooting gas and dust toward the Sun, you're creating thrust in that direction, which means you're slowing yourself down relative to your orbital motion. If you flip that jet to point away from the Sun, you're now accelerating in the opposite direction. For an object on a precisely calculated trajectory through the solar system, such a reversal should show up in its motion. The orbit should deviate from the purely gravitational path predicted by Newton's and Einstein's equations. The object should be somewhere slightly different than where pure celestial mechanics says it should be. But here's the puzzle. 3I-ATLAS isn't showing significant non-gravitational acceleration. Its path matches what gravity alone predicts, within the margins of measurement error. That means either the jets are perfectly balanced, pushing equally in all directions so the forces cancel out, or the object is so massive that the recoil from its outgassing is negligible compared to its inertia. Or something else entirely is going on that we haven't considered? Let me show you what makes this observation so unusual. On your screen now, imagine vectors, arrows showing the direction of material ejection. In July, that arrow points sunward against the flow of solar radiation that normally pushes comet tails away. Then watch as we advance through time. August, early September, late September. The sunward arrow fades. A new arrow grows, pointing exactly opposite, away from the sun. The comet's position relative to Earth and the sun changes during this time, yes, but not in a way that would create this apparent reversal through projection effects alone. Astronomers have annotated these images with the geometry overlaid. Earth here, sun there, comet following this trajectory. The viewing angle does change, but when you correct for that perspective shift, when you account for how projection can fool the eye, the reversal remains. Something physical changed about where and how this object was emitting material into space. The immediate question everyone wants answered is whether we're witnessing normal comet behaviour, just unusually dramatic, or whether 3I-ATLAS is doing something that requires a different kind of explanation. The conservative interpretation suggests compositional changes as the comet heats up approaching the sun. Different ices sublimate at different temperatures. As the outer layers heat and vaporize, deeper layers with different chemical makeup get exposed. This could, in principle, change the pattern of outgassing enough to flip which direction dominates. But there's another interpretation, one that sounds like science fiction but comes from serious scientists publishing in peer-reviewed literature. What if this isn't random outgassing at all? What if the reversal is controlled, deliberate, a maneuver executed by an object that isn't entirely natural? Before you dismiss that as tabloid speculation, understand who's making this argument and what evidence they're citing. The engineered probe hypothesis, as it's carefully termed in academic papers, rests on observable signatures. If the sun-facing emission was braking thrust and the subsequent away-facing tail is forward acceleration, timed around the comet's closest approach to the sun, then we're looking at behaviour that resembles trajectory adjustment more than passive ice sublimation. The stakes here are larger than one unusual comet. If 3I-ATLAS is natural but exhibiting behaviour we've never documented before, it expands our understanding of what interstellar objects can do, how they're composed, what happens when bodies from other star systems venture through our neighbourhood. If it's something else, if those engineered object signatures hold up under scrutiny, then we're facing a discovery that would rank among the most consequential in human history. We have weeks, not years, to find out. The object reaches perihelion, its closest approach to the sun, on October 29, 2025. That's the moment of maximum heating, maximum stress, maximum activity. What happens to 3I-ATLAS during that passage will either confirm it's an exotic but natural comet, or deepen the mystery into something that demands answers we're not ready to give. Part 2. Quantitative Constraints and Dynamics. The numbers tell their own story, and that story starts with mass. Between July and October 2025, 3I-ATLAS shed approximately 2 million metric tons of material into space. Think about that figure for a moment. 2 million tons. That's the mass of roughly 3 Empire State Buildings evaporating into the void, carried away by solar heating and internal pressure over just a few months. Astronomers derived this number through careful measurement of brightness and composition. When dust and gas scatter sunlight, they reveal themselves through the glow they produce. Telescopes measure that brightness at different wavelengths, applying conversion factors that account for particle size, reflectivity, and geometric distribution. They integrate that brightness over time, tracking how much material continuously streams away from the nucleus. The result is a mass loss rate, grams per second becoming kilograms per day, becoming millions of tons over the observation period. That mass loss creates thrust. It has to. Every action produces an equal and opposite reaction, Newton's third law applying as reliably in deep space as it does here on Earth. When a comet vents gas and dust into space, the nucleus recoils like a rocket engine firing. For typical comets, this rocket effect is measurable. It shows up as deviations from the purely gravitational orbit, tiny accelerations that astronomers catalogue as non-gravitational forces in their orbital solutions. But 3I-ATLAS shows minimal non-gravitational acceleration. Its trajectory matches what gravity alone predicts. The orbital residuals, those small differences between where it should be and where it actually is, remain within the noise of measurement uncertainty. This absence of detectable recoil places powerful constraints on what's happening. Let me walk you through the calculation that reveals why this matters. If you know the rate at which mass is being ejected and, the velocity of that material as it leaves the nucleus, you can calculate the thrust force. Thrust equals mass flow rate times exhaust velocity, the fundamental rocket equation. For a comet, exhaust velocity depends on what's sublimating, with different volatiles expanding at different speeds. Carbon dioxide molecules heated by the sun rush away faster than heavier dust grains dragged along by the gas flow. Take reasonable estimates for these velocities, something in the range of a few hundred meters per second for gas, slower for dust. Multiply by the mass loss rate derived from observations. You get a thrust force. Now calculate the acceleration that force would produce. Force divided by mass equals acceleration. And here's where the constraint bites. For the observed lack of orbital perturbation to make sense, the nucleus must be massive enough that this thrust barely budges it. The minimum mass estimate comes out to approximately 33 billion metric tons. 33 billion. The uncertainty range is large because we don't know the exact dust velocity, don't know how much of the ejection is directional versus isotropic, don't know the precise ratio of gas to dust. But even accounting for those unknowns, the lower limit sits comfortably in the tens of billions of tons. What does an object with that mass look like? If you assume a density similar to typical comet nuclei, somewhere around 600 kilograms per cubic meter, that porous mixture of ice and dust and rock, you can back out a size. The calculation suggests a body several kilometers across, comparable to some of the larger comets we've studied up close with spacecraft. Comet Hale-Bopp, that spectacular visitor from the mid-90s, had a nucleus estimated at roughly 60 billion tons. Comet Halley, the most famous periodic comet, masses about 220 billion tons. 3I-ATLAS sits on the lower end of that range, but still qualifies as a substantial body. The uncertainty bands deserve attention because they reveal how much we don't know. If the dust particles are moving faster than assumed, the mass estimate drops. If the outgassing is more anisotropic, focused into narrow jets rather than distributed evenly, the recoil might be directionally biased in ways that partially cancel out, making the mass constraint weaker. If a larger fraction of the lost mass is fine dust rather than gas, the momentum transfer changes because dust accelerates more slowly and might not contribute as much thrust per unit mass. Imagine a Monte Carlo simulation on your screen now. Thousands of model runs exploring different combinations of parameters within their plausible ranges. Each run generates a mass estimate. The distribution of results shows a peak around 33 billion tons, but spreads across a factor of 3 in either direction. This is the honest uncertainty of astronomical inference, translating observed light into physical properties across hundreds of millions of kilometers of space. 3 scenarios could explain the minimal non-gravitational acceleration. First, the object is genuinely massive enough that its outgassing thrust is negligible. This is the straightforward interpretation, requiring nothing exotic, just a big comet shedding material at a rate proportional to its size. Second, the outgassing might be unusually symmetric, jets firing in multiple directions such that the net force averages close to 0. Some comets do this, with active regions on different parts of the surface producing thrust vectors that partially cancel. Third, something non-cometary might be happening, some mechanism that doesn't follow the standard sublimation-driven model. That third option is where things get speculative, but speculation grounded in the observational constraints. If 3I-ATLAS were maneuvering using some controlled propulsion system, you'd want the thrust to be balanced or variable in ways that don't produce random orbital changes. An engineered object maintaining a specific trajectory would minimize detectable non-gravitational forces outside its intended maneuvers. The math doesn't prove this interpretation, but it doesn't rule it out either, which is enough to keep the question alive. The size estimate also matters for another reason. Interstellar space is hostile. Cosmic rays bombard any object travelling through the galaxy. Over millions or billions of years, those high-energy particles erode surface material, alter chemical composition, create radiation damage. Smaller objects suffer more because they have less mass to absorb the punishment relative to their surface area. A body several kilometers across has been large enough to survive its interstellar journey relatively intact, maintaining a substantial volatile inventory that can now activate as it passes through the solar system's warmth. Compare this to 1I/Oumuamua, the first confirmed interstellar visitor, which was probably only hundreds of meters in size based on brightness and assumed composition. 1I/Oumuamua showed significant non-gravitational acceleration despite no detected outgassing, a puzzle that generated years of debate and multiple competing explanations. 3I-ATLAS, being much larger, should produce observable outgassing if it contains volatiles, and it does. But the absence of corresponding orbital changes, given that large mass loss, creates its own puzzle. What happens next depends on perihelion. The close solar passage will heat the nucleus to maximum temperature, potentially triggering fresh outgassing from previously dormant areas. If the mass loss rate increases dramatically, as often happens when comets around the Sun, we'll get better constraints on the nucleus properties from the enhanced activity. If the orbital residuals suddenly jump, showing clear non-gravitational acceleration during or after perihelion, that tells us something changed about the outgassing pattern. The data collected in the next few weeks will either tighten these mass constraints or reveal new anomalies that demand explanation. Part 3. Physical and compositional model. The physics of ice wants to explain everything if you'll let it. Abraham Loeb and Andrew Quito, two astronomers who've spent considerable time thinking about 3I-ATLAS, published a model that attributes the jet reversal to compositional changes in the sublimating volatiles. Their argument flows from first principles about how different ices behave at different temperatures and distances from the Sun. Start with carbon dioxide ice. It sublimates, transitions directly from solid to gas, at temperatures far below the freezing point of water. Even at the chilly distances beyond 3 or 4 astronomical units from the Sun, carbon dioxide molecules can break free from their crystalline lattice and stream into space. The gas expands rapidly, and as it does, it entrains dust particles, dragging them along through collisions and momentum transfer. These dust grains, once liberated, become subject to solar radiation pressure, the gentle but persistent push of sunlight that affects small particles more strongly than large ones. Now consider what happens as the comet moves inward, closer to the Sun's warmth. The carbon dioxide sublimates more vigorously, but eventually the surface layers rich in carbon dioxide get depleted. Deeper material becomes exposed, and that deeper material has a different composition. Water ice dominates, mixed with refractory dust, the rocky and carbonaceous particles that don't sublimate at all, but rather get left behind or mechanically released as the ice around them vaporizes. Water ice requires higher temperatures to sublimate efficiently. It activates closer to the Sun, in the inner solar system where heating becomes intense. The dust released by water sublimation has different properties than dust entrained by carbon dioxide. The grain size distribution might differ. The release velocity might be lower because water vapour expands less energetically than carbon dioxide. The survival distance, how far the particles travel before they either break down under solar heating or get swept away by radiation pressure, changes based on composition and size. Here's where the model gets clever. Loeb and Quito argue that this transition from carbon dioxide-dominated to water-dominated sublimation can flip the apparent direction of emission. In the carbon dioxide phase, smaller ice-coated grains with short lifetimes scatter efficiently at optical wavelengths. These particles, released early in the comet's approach, might create a forward-scattered glow visible from Earth's viewing geometry, appearing as a sun-facing anti-tail. As the regime shifts to water and refractory dust, larger particles with different scattering properties dominate. These create a more traditional tail pushed away from the Sun by radiation pressure. The timing aligns with observations. 3I-ATLAS was around 3 to 4 astronomical units from the Sun when the anti-tail was most prominent. That's precisely the distance range where carbon dioxide sublimation should be active, but water ice remains mostly dormant. As the comet descended through 3 astronomical units, heading toward its October perihelion at 1.356 astronomical units, the transition to water-dominated activity would naturally occur. The Nordic optical telescope images capturing the tail reversal in August and September span exactly this transitional period. Imagine a cross-section of the comet's nucleus on your screen. The outer layers, exposed to space during the object's long interstellar journey, are enriched in carbon dioxide ice because it's more volatile, more likely to have been retained near the surface. Deeper down, water ice dominates because it's more refractory, less prone to sublimate during the object's cold storage between stars. As solar heating creates a sublimation front that advances into the nucleus, that front crosses the compositional boundary. The outgassing regime changes, and with it, the observable properties of the coma and tail. This model has precedent in solar system comet behaviour. Astronomers have documented comets showing seasonal variations in activity, with different regions turning on and off as they rotate, and as their heliocentric distance changes. Comet Hale-Bopp, that giant visitor from 1997, displayed multiple distinct jets from different active areas, each releasing material with slightly different composition and timing. The lesson from decades of comet studies is that these objects are heterogeneous, layered, capable of surprising behaviour as thermal waves penetrate their interiors. But 3I-ATLAS seems more abrupt in its transition than typical solar system comets. The reversal happened over weeks rather than months or years. That rapidity suggests either a sharp compositional boundary inside the nucleus, or an unusual geometry of active regions. Perhaps the initial sun-facing activity came from a specific location on the surface that became inactive as it heated past some threshold, while simultaneously a different region on the opposite side activated. Comet nuclei are irregular bodies, often with complex topography. Cliffs, basins, and fractured terrain can focus outgassing in ways that don't reflect the average surface properties. The model makes predictions that can be tested. If the compositional transition explanation is correct, spectroscopic observations should show the predicted change in gas composition. Early observations, when the anti-tail was prominent, should show relatively strong carbon dioxide emission lines. Later observations, after the reversal, should show enhanced water vapour and possibly other volatiles like carbon monoxide that sublimate at intermediate temperatures. The dust-to-gas ratio should also change, with more refractory material in the later stages. Some observational evidence supports this picture. Reports indicate that spectroscopic follow-up detected compositional changes consistent with evolving volatile activity. The relative strength of different emission features shifted between July and September, matching what you'd expect if the dominant sublimating species changed. But the data remains sparse enough that alternative interpretations can't be decisively ruled out. Spectroscopy of faint, fast-moving objects is challenging. Signal-to-noise constraints mean you can't always see the subtle spectral lines that would clinch the case. The grain size distribution adds another layer of complexity. Loeb and Quito's model explicitly considers how particle size affects dynamics. Small grains, sub-micron to micron scale, are strongly coupled to gas flow and get accelerated to high velocities. They also have short survival times because solar heating sublimates any volatile coating quickly. Large grains, tens to hundreds of microns, are less coupled to gas, move more slowly and survive longer. The balance between these populations determines what you see and where you see it in the coma and tail. The model suggests that during the carbon dioxide phase, small ice grains dominate the optical signature, creating a compact, bright emission that under certain viewing geometries appears sun-facing. During the water dust phase, larger refractory grains dominate, creating a more extended tail that follows the classical radiation pressure-driven pattern. The abruptness of the transition reflects the relatively narrow distance range over which the compositional boundary gets crossed. Weaknesses in this explanation exist, and honest scientists acknowledge them. The required compositional stratification, though plausible, hasn't been directly observed. We haven't drilled into 3I-ATLAS to confirm it has a carbon dioxide-rich outer layer over a water-rich interior. We're inferring structure from behaviour, always a risky proposition. The anisotropy of emission, whether jets are focused or diffuse, remains uncertain, and the precise grain size distribution, which is critical to the model's predictions, is poorly constrained by current observations. What observations would definitively confirm or refute this model? High-resolution imaging showing multiple active regions turning on and off would help. Time-resolved spectroscopy, capturing the moment of transition in detail, would constrain the sublimation chemistry. Polarimetric measurements revealing changes in dust properties would test the grain size predictions. And most critically, continued monitoring through and after perihelion will show whether the anti-solar tail persists, strengthens, or gives way to new behaviour as the comet experiences peak heating. The compositional model represents the conservative interpretation, the one that requires no new physics, no exotic assumptions, just the complex but understood behaviour of ice and dust under solar radiation. It's the explanation most comet scientists would favour, until forced otherwise by irreconcilable observations. But as we'll see, not everyone is convinced that ice tells the whole story. Part 4. The alternative. Controlled motion and engineered probe hypothesis. Now we shift firmly into speculative territory, but we do so with a scientist's rigour, not a tabloid's breathlessness. Abraham Loeb and Adam Hibbard, in a series of public statements and technical analyses, have raised the question that most astronomers carefully avoid. What if the jet reversal isn't natural at all? What if 3I-ATLAS is executing a controlled manoeuvre, adjusting its trajectory using propulsion that only superficially resembles comet outgassing? The hypothesis rests on timing and directionality. If the sun facing anti-tail, observed in July, acted as braking thrust, pushing the object slightly toward the sun, and therefore slowing its orbital motion, then the subsequent anti-solar tail could represent forward thrust, accelerating the object outward as it swings around perihelion. Such a manoeuvre would resemble trajectory correction, the kind of burn a spacecraft makes to fine-tune its path through the solar system. Before you dismiss this as wild speculation, consider what observational signatures would support it. First, sustained non-gravitational acceleration beyond what sublimation models predict. If the thrust continues longer than thermal models say the outgassing should last, or if the acceleration is larger than the mass loss rate can explain, that's an anomaly. Second, repeatable reorientation of the jet axis. Natural comets can have multiple jets, but they're tied to the body's rotation and illumination pattern. If 3I-ATLAS showed jet direction changes that don't correlate with rotation or solar heating, that's strange. Third, spectral anomalies. If the emitted material has composition inconsistent with typical cometary volatiles, that demands explanation. So far, none of these smoking gun signatures have been definitively detected, but the observations are incomplete. The object is faint, moving fast and difficult to track continuously. Gaps in the data mean we can't rule out brief episodes of unusual acceleration or spectral features that appeared when no telescope was watching. The absence of evidence is not evidence of absence, a phrase that applies here more than in most astronomical puzzles. Testing the engineered object hypothesis requires long-term astrometric monitoring. Astronomers need to measure the object's position precisely, repeatedly, over months and years. They then fit those positions to orbital models, comparing purely gravitational trajectories to models that include non-gravitational terms. The residuals, differences between predicted and observed positions, reveal whether something beyond gravity is affecting the motion. Small random residuals are normal, caused by measurement errors and minor outgassing. Large systematic residuals indicating sustained thrust in a consistent direction would be extraordinary. Polarimetric observations could help too. Dust particles scatter light, and that scattering produces polarization patterns that depend on grain size, shape, and composition. Natural cometary dust has characteristic polarization signatures that vary with phase angle, the viewing geometry relative to the Sun. If 3I-ATLAS produces polarization inconsistent with known dust types, that's a clue. Similarly, high-resolution spectroscopy might reveal emission or absorption lines from materials not expected in comets. Metals, complex organics, anything that hints at processed or manufactured composition, rather than primitive solar system or interstellar ices. Another test involves trajectory analysis. Is the orbit of 3I-ATLAS special in any way? Does it approach the inner solar system at an angle or speed that seems too convenient, too carefully chosen? Interstellar objects have random trajectories determined by their ejection from their home systems and their path through the galaxy. If 3I-ATLAS's orbit shows fine-tuning, that raises eyebrows. However, defining what constitutes suspicious fine-tuning is subjective. With a sample size of only a few known interstellar visitors, we don't yet know what the typical distribution of orbits should look like. The community's reaction to this hypothesis has been mixed, leaning towards skepticism. Most astronomers prefer mundane explanations until forced otherwise. The history of supposed anomalies that turned out to be natural is long. Pulsars were briefly thought to be alien beacons until neutron star physics explained them. Fast radio bursts generated exotic speculation until observations pinned them to astrophysical sources. The null hypothesis, that 3I-ATLAS is a weird but natural comet, carries strong prior probability. Yet Loeb and his collaborators argue that dismissing the possibility without testing it is unscientific. Science advances by considering hypotheses, even uncomfortable ones, and designing observations to rule them in or out. The discovery of extraterrestrial technology would be monumental, so monumental that it justifies more scrutiny than we'd give most fringe ideas. The cost of false negatives, missing a real techno-signature because we didn't look carefully enough, is arguably higher than the cost of false positives, spending effort on natural objects we mistakenly thought might be artificial. This debate touches on the sociology of science. How do researchers balance open-mindedness against the risk of being wrong in spectacular, career-damaging ways? How does the community handle claims that blur the line between legitimate scientific inquiry and sensationalism? Loeb's prominence, his willingness to engage with media and public, has amplified these questions. Some colleagues appreciate his advocacy for techno-signature research, seeing it as necessary to secure funding and attention. Others worry that premature speculation undermines credibility and makes serious SETI work harder. The risk-reward calculus is stark. If 3I-ATLAS is natural, which is likely, then this whole exercise confirms what we already suspected about interstellar comets, and maybe teaches us something new about compositional diversity. If it's artificial, even if that probability is tiny, we're staring at the most consequential discovery in human history. First contact, or at least first detection, of technology from beyond Earth. That possibility, however remote, justifies serious follow-up. What would confirmation look like? You'd need multiple independent lines of evidence converging. Sustained acceleration inconsistent with outgassing. Spectral features implying manufactured materials. Perhaps radio or infrared emissions at frequencies and modulation patterns that can't be explained by thermal processes. You'd need observations from multiple observatories, independent teams analysing the data, rigorous statistical analysis ruling out instrumental artefacts and natural explanations. The standard for accepting such a claim would be, and should be, extraordinarily high. Proposed follow-up concepts include dedicated space missions. Loeb has suggested fast flyby probes, launched on high-energy trajectories to intercept 3I-ATLAS after perihelion and take close-up images, spectra, and particle samples. Such missions would be expensive and technically challenging, requiring short development timelines to catch the object before it races back out of the solar system. But compared to the potential payoff, the investment might be justified. The problem is time. By the time funding, approval and construction happen through normal channels, the object will be gone. You'd need rapid response mission architecture, something the space community hasn't yet developed for interstellar targets. Another approach involves using existing assets. Ground-based telescopes can continue tracking. Space telescopes, if their schedules allow, could provide higher resolution and sensitivity. Radio observatories could listen for transmissions. Even if 3I-ATLAS isn't deliberately broadcasting, it might emit radio noise from charged particle interactions with its surface or any internal electronics. SETI protocols developed for listening to stars could be adapted to point at this nearby moving target. The timeline matters. Perihelion on October 29th will subject the object to maximum heating and stress. If it's a passive comet, we'll see increased outgassing, possibly fragmentation if structural weaknesses exist. If it's something else, the close solar passage might trigger systems that have been dormant during the cold approach. The weeks surrounding perihelion are the critical observation window. After that, 3I-ATLAS will, after that, 3, race back toward interstellar space. Its brightness will fade as distance from the sun increases. Eventually it will be too faint for all but the largest telescopes to track, and then it will vanish from human view forever, unless we send something after it. The engineered probe hypothesis feels like science fiction, and maybe it is. Maybe we're seeing patterns where none exist, projecting human notions of spacecraft maneuvers onto random ice sublimation. But the only way to know for certain is to gather more data, test the predictions, and follow the evidence wherever it leads. That's the scientific method, and it applies whether we're studying rocks, stars, or things that might be neither. Part 5. Observational stakes and timeline. The clock is ticking louder now, each day bringing us closer to the moment that will either explain 3I-ATLAS or deepen its mystery into legend. Perihelion arrives on October 29th, 2025, when the comet reaches its closest point to the Sun at approximately 1.356 astronomical units. That's about 203 million kilometres, well inside Earth's orbit, but still a safe distance where solar heating intensifies dramatically. Perihelion is the crucible. Everything we've discussed, every model and speculation and measurement, will be tested during the hours and days surrounding that closest approach. The sun's radiation will batter the nucleus at maximum intensity. If the object contains volatiles, they'll sublimate furiously. If structural weaknesses exist, the thermal stress and internal pressure might cause fragmentation. Astronomers have watched comets break apart at perihelion before, dramatic disintegrations that reveal internal structure and composition. The observational challenges are considerable. Perihelion places 3I-ATLAS relatively close to the Sun as viewed from Earth, meaning observations require careful timing to avoid daytime sky and the glare of our star. Ground-based telescopes will have narrow windows before dawn or after dusk when the comet is visible above the horizon, but the Sun is sufficiently below. Space telescopes have advantages here because they are not limited by Earth's day-night cycle, but even they must contend with bright background and potential damage from pointing too close to the Sun. The Hubble Space Telescope, which captured that striking July image, operates under strict solar avoidance angles. It can't point within a certain zone around the Sun without risking damage to its sensitive instruments. Scheduling observations of 3I-ATLAS requires careful planning to catch the object when it's far enough from the Sun in the sky to be safe. The Nordic Optical Telescope and other ground facilities face similar but different constraints, tied to twilight and seasonal viewing windows. Then there's the Mars flyby on October 3rd, when 3I-ATLAS passed within range of the red planet. Did Mars orbiters capture images? The high-resolution imaging science experiment, known as HiRISE, aboard the Mars Reconnaissance Orbiter, has taken incredible close-ups of Martian surface features and occasionally turns to look at passing comets. If HiRISE or other Mars-orbiting cameras imaged 3I-ATLAS, those pictures would provide an invaluable different viewing angle, helping resolve ambiguities in Earth-based observations. But Mars orbiter time is precious, allocated months in advance for surface science. Whether anyone secured approval to target this fast-moving interstellar visitor remains to be seen. The real payoff comes after perihelion. As 3I-ATLAS swings back outward, its brightness will initially remain high due to the fresh outgassing triggered by solar heating. This is the period when astrometric precision matters most. Measure the object's position every few days, track how its motion deviates from the pre-perihelion orbit. If non-gravitational acceleration suddenly appears or changes magnitude, that tells you something happened during or because of the perihelion passage. December 19th, 2025 marks another critical date. Earth closest approach. At approximately 1.80 astronomical units, about 270 million kilometres, the comet will be at its nearest to our planet. That's still far, but it's close enough for detailed observations. Large ground-based telescopes can capture high-resolution images and spectra. The James Webb Space Telescope, if its schedule permits, could provide infrared spectroscopy revealing composition details invisible in optical wavelengths. Spectral lines of water, carbon dioxide, carbon monoxide, methane, ammonia, all the common cometary volatiles, plus any exotic species, would appear in JWST's data. The timeline also includes danger zones, periods when observations are difficult or impossible. Solar conjunction, when the comet appears too close to the Sun from Earth's perspective, creates blackout periods. During conjunction, radio communication can be difficult, solar interference drowns out faint signals, and optical telescopes can't safely point in that direction. 3I-ATLAS will pass through conjunction phases as its orbit carries it across our line of sight to the Sun. Those gaps in coverage mean we might miss brief events, transient brightening or changes in morphology that appear and fade while no one is watching. Brightness evolution adds uncertainty. As the comet moves away from the Sun post-perihelion, it will fade. The rate of fading depends on how active it remains. If outgassing shuts down quickly, brightness drops rapidly, soon rendering the object too faint for all but the largest telescopes. If activity persists, driven by subsurface heat retained from perihelion or delayed volatile release, the comet could remain observable longer. Historical comets show enormous variation in their post-perihelion behaviour. Some fade into obscurity within weeks. Others remain active for months, their tails gradually shrinking but still visible. coordination among observatories will be essential. Transient alert networks, originally designed for supernovae and other astrophysical events, can be adapted to track 3I-ATLAS. When one telescope detects a sudden change, alerts go out to others, triggering follow-up observations. This kind of multi-facility coordination has become standard in time-domain astronomy. Gravitational wave detections, for instance, trigger worldwide campaigns to observe the electromagnetic counterparts. 3I-ATLAS doesn't have the same immediacy, but the principle applies. Spectroscopic capacity is the bottleneck. Taking a spectrum requires concentrating the object's faint light into a narrow slit and dispersing it across a detector. That process takes time and reduces signal compared to direct imaging. For a faint, fast-moving target, you need a large telescope, good tracking, and long integration times. Few facilities can do this on demand. The queue for major instruments fills months in advance. Getting directors discretionary time, reserved for urgent targets of opportunity, requires convincing proposals and a bit of luck. There's also the matter of what to look for. If you're testing the natural comet hypothesis, you focus on composition, morphology, and brightness evolution. If you're testing the engineered object hypothesis, you add radio observations, search for unusual spectral lines, look for polarization anomalies, and monitor for any sign of non-random behavior. Each requires different instruments and observing strategies. Resources are finite. Choices must be made about which tests to prioritize. Public interest adds another dimension. 3I-ATLAS has captured attention beyond the usual astronomy circles. News articles, social media discussions, even government agencies asking questions. That attention can help secure telescope time and funding, but it also creates pressure. Astronomers must balance careful science against the demand for quick answers. Rush to conclusions and you risk being wrong. Wait too long and the object fades beyond reach before decisive data are collected. By December 19th, we'll have months of post-perihelion data. The trajectory will be precisely measured. Spectroscopic observations will have characterized composition changes. High-resolution imaging will have documented morphological evolution. The combination of all these data streams will either converge on a coherent natural explanation or leave us with residual anomalies that can't be easily dismissed. That convergence or lack thereof determines what happens next. If the data confirm the compositional model, if everything fits the carbon dioxide to water transition narrative, then 3I-ATLAS becomes a fascinating but ultimately understood interstellar comet. Papers get published. Conferences hold sessions. The object is added to. A growing catalogue of visitors from beyond our solar system. A data point in studies of galactic small body populations. Science moves forward, slightly richer for the experience. If anomalies persist, if the non-gravitational acceleration doesn't match sublimation models, if spectral features remain unexplained, then the conversation changes. Mission proposals get serious consideration. Dedicated observation campaigns extend beyond December. Perhaps international collaboration brings more resources to bear. The object hasn't left the solar system yet. At its current trajectory, it will take years to recede beyond Saturn's orbit, though it will be very faint by then. But if the stakes are high enough, if we genuinely suspect artificiality, the investment in continued monitoring becomes justified. The next few months are a countdown not just to perihelion and Earth approach, but to a decision point in how we think about interstellar space. Are we alone in producing technology that travels between stars? Or does the galaxy harbour others who send their proxies, intentionally or accidentally, into neighbouring solar systems? 3I-ATLAS might answer that question, or it might leave us hanging with inconclusive data and competing interpretations. Either way, the clock is ticking, and by the time winter solstice arrives, we'll know far more than we do today. Part Point 6. Observational Systematics and Projection Pitfalls. Not every strange thing in the sky is actually strange. Sometimes what looks extraordinary is just ordinary physics viewed from an unusual angle. This is the first lesson of observational astronomy, learned and relearned across centuries. The apparent retrograde motion of Mars confused ancient astronomers until heliocentric models explained it as a perspective effect. The canals of Mars turned out to be optical illusions, the human eye connecting random features into patterns, and many comets have appeared to flip their tails when in reality only our viewing angle changed. The question facing 3I-ATLAS is fundamental. Are we witnessing intrinsic jet reversal or a projection illusion? The distinction matters enormously. An intrinsic flip demands physical explanation, something changing inside or on the comet. A projection effect is just geometry, Earth's motion relative to the comet creating an apparent reversal, while the actual ejection pattern remains constant. Let me explain how projection effects work. A comet ejects material in three-dimensional space, but we observe it as a two-dimensional projection on the sky. Our line of sight collapses depth information, making it hard to distinguish between material moving toward us, away from us, or perpendicular to our view. As Earth orbits the Sun and the comet follows its own trajectory, the viewing geometry constantly changes. What appeared to be directed one way can seem to flip as our perspective shifts. The classic case is the anti-tail phenomenon, known for over a century. When Earth crosses the orbital plane of a comet, dust particles that lag behind the nucleus along its orbit appear to point sunward, creating an anti-tail. This happens because we're viewing the dust trail edge-on. The particles aren't moving toward the Sun, they're trailing the comet along its path, but from our temporary viewing angle, they project as a forward spike. Then, as Earth continues moving, crossing out of the comet's orbital plane, that anti-tail vanishes, and the normal tail becomes prominent again. Astronomers have sophisticated methods for distinguishing real from apparent changes. Vector tomography uses observations from multiple dates and viewing angles to reconstruct the three-dimensional distribution of material. If you watch the comet from enough different perspectives, you can invert the problem, solving for the actual spatial structure that produces the observed two-dimensional projections. This technique works best when viewing geometry changes substantially, giving you diverse angles to triangulate from. Polarimetry provides another diagnostic. Dust particles scatter sunlight, and that scattering produces polarization. The degree and direction of polarization depend on the scattering angle, the angle between incoming sunlight, the dust particle, and our line of sight. Different viewing geometries produce different polarization signatures even if the dust distribution remains constant. Measure polarization over time, and you can test whether observed morphology changes are consistent with static dust, illuminated from varying angles, or require actual redistribution of material. Time-sequenced imaging helps too. If you capture images frequently enough, you can watch individual features evolve, tracking their motion across the sky and relative to the nucleus. Features that are truly new, genuinely changing emission patterns, will appear and evolve in ways inconsistent with simple projection of static structures. Features that are projection artifacts will shift predictably as viewing geometry changes, following mathematical models of perspective transformation. Historical examples inform this analysis. Comet Arend-Roland in 1957 displayed a spectacular anti-tail as Earth crossed its orbital plane. Observers initially marvelled at this sun-facing spike, some speculating about unusual physics. Careful geometric analysis showed it was entirely projection, dust distributed along the comet's orbit appearing to point forward due to viewing angle. More recently, Comet Lulin in 2009 showed anti-tail features that similarly resolved into geometric effects. Now apply these lessons to 3I-ATLAS. Between July and September, Earth's position relative to the comet changed significantly. Both objects were moving, Earth in its nearly circular orbit, 3I-ATLAS on its hyperbolic trajectory plunging sunward. The geometry shifted, altering phase angles, scattering angles, and the projection of any three-dimensional structures in the coma onto the two-dimensional sky. The Nordic Optical Telescope team, who tracked the comet through this period, would have been aware of projection pitfalls. Their analysis presumably included geometric modelling, testing whether the observed changes could be explained by Earth's changing position alone. The fact that they reported an intrinsic jet reversal suggests their models ruled out pure projection effects, but ruling out requires assumptions about the dust distribution, ejection velocities, and other parameters. Uncertainty in those assumptions leaves room for alternative geometric explanations. One way to test this is simulation. Generate a model comet with static dust ejection, some fixed pattern of jets or isotropic outgassing. Calculate what Earth-based observers would see at different dates as viewing geometry changes. Compare those predictions to actual observations. If the match is good, projection effects dominate. If predictions fail to reproduce observed features, intrinsic changes are required. The challenge is that real comets aren't static. Even if the jet reversal is projection, the comet is still evolving. Outgassing rates change as heliocentric distance decreases. Dust production varies. Active regions turn on or off. Rotation carries different surface areas into and out of sunlight. Separating viewing geometry effects from genuine activity changes requires careful modelling of both. Polarimetric data, if available, would help tremendously. Reports haven't detailed whether polarimetry was performed on 3I-ATLAS during the critical July to September period. If such data exist, they could constrain dust grain properties and scattering geometry, tightening limits on projection versus intrinsic interpretations. If polarimetry wasn't done, that's a gap that future observations might fill, though by then the geometry will have changed again. Another consideration is the abruptness of the transition. Projection effects tend to be smooth, gradual, as viewing geometry continuously evolves. A sudden flip, happening over days rather than weeks, suggests something intrinsic. But defining sudden versus gradual is subjective when observation cadence is irregular. If you image once a week, a change that happened over 3 days appears sudden, while the same change sampled daily might look smoother. Multiple independent observers strengthen the case. If several telescopes in different locations with different instruments and viewing conditions all report the same transition, instrumental or observational artifacts become less likely. The Nordic Optical Telescope, Hubble, and potentially others form a cross-checking network. Consistency across platforms argues for reality over artifact. There's also the composition angle. Projection effects can't change spectral signatures. If the emitted material's chemistry shifted between July and September, that's intrinsic, not geometric. Spectroscopic follow-up reportedly detected compositional changes, supporting the physical transition model. But again, details matter. How strong were the spectral features? What uncertainties exist? Were multiple wavelengths covered, providing robust compositional diagnostics? The risk of confirmation bias looms. Once researchers believe they've found something unusual, they interpret ambiguous data to support that belief. Independent analysis by teams with no stake in the outcome provides a check. Have skeptics examined the data? Do alternative explanations exist that haven't been fully explored? The scientific process requires adversarial collaboration, where different groups challenge each other's interpretations, forcing stronger evidence and better arguments. By the time you account for all these factors, viewing geometry, dust dynamics, instrumental effects, observational cadence, you realise how difficult it is to claim certainty. The honest answer is that projection effects probably don't explain the full extent of the observed reversal, but they might contribute. The intrinsic jet flip interpretation is likely correct, but with acknowledged uncertainties, and those uncertainties matter when deciding how exotic an explanation to invoke. Part 7. Small particle versus large particle dynamics and dust size sorting. Dust grains are not all created equal, and their inequality determines much of what we see when we look at comets. The physics governing these tiny particles, fragments of rock and ice ranging from nanometers to millimeters, explains why comet tails stream away from the sun, why some comets appear dusty while others seem gas-rich, and potentially why 3I-ATLAS showed sun-facing emission before its tail reversed. Start with the beta parameter, a dimensionless number that captures the ratio of solar radiation pressure to solar gravity acting on a dust grain. Small particles have high beta, meaning sunlight pushes them more strongly than gravity pulls them. Large particles have low beta, feeling gravity more and light pressure less. The crossover happens around micron scales, with exact values depending on composition, shape, and distance from the sun. For very small grains, submicron particles, beta can exceed 1. That means radiation pressure overwhelms solar gravity. These particles, once released from the comet, accelerate away from the sun faster than they would fall inward. They form the classical comet tail, that glowing streamer extending millions of kilometers anti-sunward. The smaller the grain, the faster it accelerates, the straighter the tail appears. Larger grains with beta less than 1 follow more curved paths, a compromise between their orbital motion and the outward push of sunlight. Now consider what happens to grains with very low beta, particles tens or hundreds of microns across. These grains barely feel radiation pressure. They're released from the comet with some initial velocity, the kick from sublimating gas, but then follow nearly ballistic trajectories dominated by their orbital motion around the sun. These particles form dust trails, extended structures that trace the comet's orbit, often lagging behind the nucleus because they were released earlier when the comet was at a different point in its path. Under certain geometric conditions, these large low-beta grains can appear to point sunward. If Earth's viewing angle aligns just right, the trailing dust, spread along the comet's orbit behind where it currently sits, projects as a forward-pointing feature. This is the mechanism behind classical anti-tails, and it's entirely geometric, requiring no actual sun-facing emission. The relevant formulae describe grain drift. A particle released from the comet at some velocity with some beta value will follow a perturbed orbit. Calculate its trajectory by integrating the equations of motion, including solar gravity and radiation pressure as vector forces. The result depends on release position, release velocity, and beta. Sum over many grains with different sizes and release times, and you build up the predicted dust distribution in three-dimensional space. Now predict what Earth-based observers see by projecting that distribution onto the sky plane. This forward modelling approach lets you test hypotheses. If you assume the comet releases dust isotropically with some velocity distribution and grain size distribution, you can predict brightness patterns and compare to observations. Matches confirm your assumptions. Mismatches indicate something's wrong with the dust properties or ejection pattern. For 3I-ATLAS, the question is whether the observed sun-facing glow in July could be explained by low beta dust in an anti-tail geometry. The answer depends on several factors. First, the comet's orbital plane and viewing geometry. Second, the grain size distribution. If most dust is small, high beta material, you won't get a strong anti-tail even with favourable geometry. If a significant fraction is large, low beta grains, anti-tails, become possible. Third, the grain lifetime. Large particles might survive longer, but they still eventually fragment or sublimate under intense solar heating. Survival time depends on composition. Ice-rich grains sublimate relatively quickly, their lifetime measured in hours to days at 1 astronomical unit from the Sun. Refractory grains, rocky particles with little volatiles, survive longer, potentially weeks or months. If 3I-ATLAS released refractory dust early in its approach, those particles could still be present, forming a trail that projects as an anti-tail when viewed edge-on. Ejection velocity matters too. Gas drag from sublimation accelerates dust off the nucleus, but the terminal velocity depends on grain size and gas production rate. Small grains reach speeds of hundreds of meters per second. Large grains might only reach tens of meters per second. Lower ejection velocities mean grains stay closer to the comet's orbit, increasing the geometric likelihood of anti-tail projections. There are thresholds to consider. Grains larger than roughly 50 microns, released with velocities less than about 100 meters per second, at heliocentric distances of 2 to 3 astronomical units, could produce sun-facing enhancements under appropriate viewing angles. But the enhancement would be relatively faint because large grains scatter less light per unit mass than small grains. You'd need substantial dust mass in large particles to create the bright anti-tail observed in Hubble's July image. The Loeb and Keto model invokes small ice-coated grains rather than large refractory ones to explain the initial sun-facing emission. Their argument is that carbon dioxide sublimation early in the approach released ice grains that forward-scattered sunlight efficiently when viewed from Earth's geometry. These grains, being small, had high beta and short lifetimes, creating a compact, bright feature that appeared sun-facing, not because of projection, but because of actual preferential emission combined with scattering properties. This interpretation shifts the explanation from orbital dust trails to active emission patterns. The grains aren't trailing from earlier epochs. They're being produced now, recently, with properties and velocities that, combined with viewing geometry, produce forward-scattered glow. As the comet transitioned to water and refractory dust, the grain population changed. Larger, darker particles replaced bright ice grains. The forward scattering diminished while classical backscattering off large grain tails grew, creating the observed reversal. Uncertainties abound. We don't know 3I-ATLAS's grain size distribution. Observations provide some constraints through brightness and colour measurements, but degeneracies exist. A given brightness could result from many small grains or fewer large grains. Spectral slope, how brightness changes with wavelength, offers clues, but interpretation requires assumptions about composition and shape. Anisotropic ejection complicates everything. If jets are concentrated, not uniform, then dust distribution is directional. Different viewing angles see different amounts of dust, even if the total production rate is constant. Rotation further modulates this. As the comet spins, jets point different directions, creating time-variable emission that couples with viewing geometry in complex ways. The dust size sorting explanation permits some anti-tail phenomena naturally, yes, but the scale and timing of 3I-ATLAS's reversal push the boundaries of what geometric effects and grain size distributions can plausibly explain. The abruptness, the brightness contrasts, the spectral changes all suggest more than passive dust trailing or projection tricks. Something changed about how and what the comet was emitting, and while dust physics contributes to understanding that change, it probably doesn't fully explain it without invoking compositional transitions or other intrinsic evolution. This matters for the broader interpretation. If dust size sorting and projection effects explained everything, the engineered object hypothesis would be unnecessary. Natural comet behaviour, well understood if complex, would suffice. But if those geometric explanations fall short, if residual anomalies remain after accounting for dust dynamics, then more exotic possibilities stay on the table. The dust physics narrows the space of viable explanations, but doesn't yet uniquely determine which explanation is correct. Part 8. Instrument and Analysis Cross-Checks. Telescopes lie, or at least they mislead if you're not careful. Every instrument carries biases, artifacts, systematic errors that can mimic real celestial phenomena. This is why astronomers obsess over cross-checks, comparing observations from different telescopes with different instruments under different conditions. If multiple independent systems see the same thing, confidence grows. If discrepancies appear, someone's detector is misbehaving or someone's analysis has gone astray. The catalogue of observatories contributing 3I-ATLAS data spans ground and space. The Hubble Space Telescope, humanity's premier optical observatory, captured that crucial July 21st image showing the sun-facing anti-tail. Hubble's Wide Field Camera 3 offers excellent spatial resolution and carefully calibrated photometry. It's been doing this for over a decade, imaging thousands of targets with well-understood performance characteristics. The Nordic Optical Telescope, a 2.5-metre ground-based instrument in La Palma, provided the July through September monitoring sequence that documented the tail evolution. Ground telescopes face challenges. Space telescopes don't. Atmospheric turbulence, weather, daylight constraints. But they offer flexibility, rapid response, and continuous access that oversubscribed space facilities can't match. The Knot has long history of cometry observations, with experienced teams knowing how to extract signal from faint moving targets. Other facilities likely contributed too. Keck Observatory in Hawaii, with its 10-metre twin telescopes, has capacity for high-resolution spectroscopy of faint objects. Gemini South in Chile offers similar capabilities in the southern hemisphere. These large aperture instruments can gather enough light from a comet's coma to disperse it into spectra, revealing compositional information through emission lines of specific molecules. Mars orbiters represent a different class of observer. The Mars Reconnaissance Orbiter's HiRISE camera, designed for sub-meter resolution imaging of the Martian surface, has occasionally turned to image comets passing near the red planet. If 3I-ATLAS was visible from Mars during the October 3rd flyby, HiRISE could have captured images from a completely different viewing angle than Earth-based telescopes. That diversity of perspective helps break degeneracies in interpreting three-dimensional structure from two-dimensional projections. The James Webb Space Telescope, though scheduled months in advance, might have dedicated time to 3I-ATLAS. JWST's near-to-mid-infrared spectroscopy excels at detecting water, carbon dioxide, carbon monoxide, and organic molecules in cometary comae. Observations at wavelengths where ice and dust have distinct signatures would constrain composition more tightly than optical data alone. Each instrument brings specific challenges. Hubble's pointing stability is excellent, but tracking fast-moving solar system objects requires careful planning. The telescope must slew to follow the target during exposure, compensating for the object's motion against the background stars. Imperfect tracking creates trailing or smearing, elongating the image in the direction of motion. That elongation could potentially mimic or mask real morphological features like jets or tails. Ground-based telescopes face atmospheric seeing, the blurring caused by turbulent air. Adaptive optic systems compensate partially, using deformable mirrors to correct wavefront distortions in real time, but correction is imperfect. Residual seeing can smooth out fine details, making sharp jets appear diffuse. Weather causes gaps in coverage. Clouds, wind, poor transparency all limit observing windows. A critical brightening or morphological change happening during bad weather goes unrecorded. Photometric calibration requires precision. Measuring brightness accurately means knowing how much light entered the telescope, correcting for atmospheric extinction, instrument throughput and detector efficiency. Different telescopes use different calibration procedures. Systematic differences of 10 or 20% are common, especially for faint extended objects like comets, where aperture choices and background subtraction affect measured brightness significantly. Background subtraction is particularly tricky for comets. The coma, that diffuse cloud of gas and dust, has no sharp edge. Deciding where the comet ends and the sky begins is subjective. Place your background annulus too close, and you include coma, underestimating its brightness. Place it too far, and you might include field stars or galaxies, overestimating background and thereby boosting the comet's measured brightness. Different observers make different choices, introducing scatter into reported photometry. Spectroscopy adds another layer of complexity. Extracting a spectrum from a faint extended source requires careful attention to slit placement, orientation, and width. The slit must be aligned with interesting features, perhaps a jet axis, to maximize signal. But the comet is moving, and morphology might be changing. A spectrum taken one night might sample a different region than one taken a week later, making direct comparison difficult. Wavelength calibration in spectroscopy uses lamp spectra with known emission lines. Small calibration errors, a fraction of an angstrom, can shift where you think a spectral feature is, leading to misidentification of molecules. Temperature and pressure changes in the instrument can introduce drifts between calibration and science exposures. Vigilance and redundant calibrations mitigate these issues but don't eliminate them. Cross-comparison between telescopes tests for systematics. If Hubble and not both see the Sun facing anti-tail in July, that feature is real, not an artifact of one instrument. If spectroscopy from Keck and Gemini both detect carbon dioxide emission, that molecular identification is solid. Consistency across platforms argues against instrumental explanations for observed features, but full consistency is rare. Observers report discrepancies, differences in measured brightness, slight morphological variations. Some of that is real-time variability. Comets do change on timescales of hours to days. Some is instrumental. Disentangling requires modelling. Simulate observations with each instrument, accounting for resolution, sensitivity, tracking errors, and seeing. Compare simulations to actual data. Residuals reveal what's unexplained by known instrumental effects. The multi-filter approach helps with wavelength dependence. Optical images in blue, green and red filters sample different parts of the spectrum. Dust and gas have different colour properties. Dust scatters sunlight, looking white or slightly reddened. Gas emission appears in discrete lines, bright in certain filters depending on which transitions are active. Comparing brightness across filters separates dust from gas, constraining composition and activity. Infrared observations complement optical. Water and carbon dioxide have strong absorption bands in the near-infrared. JWST or ground-based infrared instruments measure flux in those bands, directly quantifying volatile abundances. Thermal emission at mid-infrared wavelengths reveals nucleus temperature, which feeds into models of subsurface heat conduction and sublimation rates. Polarimetry, if performed, provides orthogonal information. Dust grains scatter light anisotropically, producing net polarization that depends on scattering angle and grain properties. Measuring polarization across multiple wavelengths and dates constrains grain size, shape, and composition independently of brightness measurements. Combined with photometry and spectroscopy, polarimetry narrows parameter space, reducing degeneracies. The question remains whether instrument and analysis systematics could fake the observed jet reversal. The answer is almost certainly no. No plausible combination of tracking errors, calibration mistakes, or background subtraction choices would create a spurious sun-facing feature in July that then vanishes while an anti-solar tail grows in September. Such consistent multi-observatory, multi-epoch signatures require a physical explanation rooted in the comet's behaviour, not telescopic artefacts. That said, quantitative details matter. How bright was the anti-tail exactly? How fast did the transition occur? What were the spectral line strengths? These numbers, with their error bars, determine which models fit and which don't. If instrumental uncertainties are larger than thought, parameter space widens, allowing more explanations to survive. If uncertainties are smaller, constraints tighten, potentially ruling out some hypotheses. Follow-up observations past perihelion will continue testing. High-cadence monitoring, images every few days, captures transient events and tracks brightness evolution precisely. Multi-wavelength coverage from UV through infrared builds a comprehensive picture of composition and thermal state. Polarimetry adds grain property constraints. Radio observations, though challenging for such a faint target, might detect molecular line emission, providing additional compositional diagnostics. The coordinated effort of the global astronomical community, multiple observatories targeting the same object with complementary techniques, is modern astronomy at its best. No single instrument tells the whole story, but together, cross-checked and calibrated, they build a dataset robust enough to distinguish real from artifact, natural from extraordinary. Part 9. Sociology of a controversial object and the Loeb effect. Science is done by humans, and humans bring all their complexity to the endeavour. Egos, ambitions, reputations, career pressures, the desire to be first, to be right, to be famous. We like to think scientific truth emerges cleanly from data and logic, but the path is messier. This is especially true when a high-profile scientist stakes reputation on a controversial idea, and that's exactly what's happening with 3I-ATLAS. Abraham Loeb is not just another astronomer. He's a former chair of Harvard's astronomy department, a prolific author, a public intellectual who engages media with enthusiasm most academics avoid. He's known for bold hypotheses, willingness to entertain ideas his colleagues dismiss as too speculative. Oumuamua, that first confirmed interstellar visitor in 2017, became a vehicle for Loeb's techno-signature advocacy. He proposed it might be a light sail, an artificial structure pushed by radiation pressure, when most astronomers favoured natural explanations like exotic ice or unusual comet activity. That Oumuamua episode divided the community. Some appreciated Loeb's willingness to think outside conventional bounds, his advocacy for considering techno-signatures seriously, his efforts to bring attention and funding to SETI research. Others cringed at what they saw as premature speculation, arguing that proposing alien artifacts without strong evidence undermines scientific credibility, makes the field look frivolous to funding agencies and the public. Now 3I-ATLAS has become the next battleground. Loeb and collaborators have published and spoken about the possibility of controlled motion, a probe executing manoeuvres. The media, predictably, amplified this angle. IFL Science ran stories highlighting the engineered object hypothesis. Mainstream news outlets picked it up. Suddenly, 3I-ATLAS is being called potentially artificial in headlines, even though the scientific consensus leans strongly toward natural explanations. This is the Loeb effect. His prominence, media connections, and rhetorical skill draw disproportionate attention to hypotheses that, proposed by less visible scientists, might circulate quietly among specialists. That attention has benefits and costs. On the benefit side, more people learn about interstellar objects. Funding agencies notice. Telescope time committees might allocate resources to follow-up. Public engagement with astronomy increases, potentially inspiring the next generation of researchers. On the cost side, sensational framing can mislead. If the public comes to believe 3I-ATLAS is probably artificial, then later when data confirm it's natural, trust in astronomical expertise might decline. Why should we believe scientists if they keep crying alien only to retract later? The damage compounds if Loeb is seen as representative of astronomers generally, when in fact he's an outlier in his willingness to publicise speculative ideas. The scientific community struggles with how to handle provocative claims. Peer review is designed to filter out weak ideas before publication, but the threshold for publication isn't the same as the threshold for broad acceptance. Papers proposing Oumuamua as artificial passed peer review, appearing in respected journals, but most astronomers didn't find them convincing. That's normal. Science thrives on disagreement. But when disagreements spill into public view, Non-experts have trouble assessing who's right. There's also the question of motive. Critics suggest Loeb's advocacy is driven partly by self-promotion, book sales, and maintaining a public profile that brings speaking fees and consulting opportunities. Defenders counter that ad hominem attacks don't address the scientific arguments. Whether Loeb benefits personally is irrelevant if his hypotheses are testable and his analyses sound. Judge the ideas, not the person. But motive does matter in subtle ways. If a scientist is incentivized to make bold claims, they might interpret ambiguous data optimistically, seeing signals where skeptics see noise. Confirmation bias, the tendency to favor information supporting existing beliefs, affects everyone but intensifies when reputation is at stake. Loeb has built a brand around technosignature advocacy. Walking back claims, admitting he was wrong, would damage that brand. This creates pressure, conscious or not, to defend hypotheses even as contradictory. Evidence accumulates. The media ecosystem amplifies everything. A measured scientific paper titled something like Potential Compositional Transition in 3I-ATLAS becomes a headline screaming, "Scientists think new comet could be alien spacecraft." Context is lost. Caveats disappear. The nuanced debate among experts reduces to binary, alien or not. That reduction does violence to the scientific process, which rarely deals in certainties, especially for unusual observations of distant objects. Funding politics enters too. SETI research has always struggled for support. Mainstream agencies are cautious about investing in searches that might never yield results. But high-profile cases like Oumuamua or 3I-ATLAS generate interest. If Loeb's advocacy helps secure funding for technosignature searches, maybe the cost in reputational risk is worth it. Better to have people arguing about whether this comet is artificial than ignoring interstellar visitors entirely. Some colleagues worry about precedent. If every unusual astronomical object triggers speculation about artificiality, the signal-to-noise ratio crashes. We've discovered thousands of exoplanets, observed countless transient events, catalogued millions of galaxies. Anomalies are common in that vast dataset. Most resolve to natural explanations once better data arrive. If we cry alien every time something doesn't immediately fit models, we dull the significance of genuine anomalies. Others argue that's precisely the point. We should be checking unusual objects for technosignatures. The cost of false positives, spending effort on natural objects we briefly thought might be artificial, is low compared to the cost of false negatives, missing actual alien technology because we didn't look carefully enough. The asymmetry favours liberal hypothesis testing. There's also the epistemic protocol question. How should the community handle speculative claims? One approach is gatekeeping, policing discourse to prevent premature speculation from reaching the public. But gatekeeping has downsides. It can stifle creativity, discourage unconventional thinking, perpetuate groupthink where everyone fears proposing ideas outside the mainstream. The opposite approach is radical openness, letting all ideas compete in a marketplace where data and argument determine winners. That sounds democratic, but risks confusion when non-experts can't evaluate competing claims. A middle path involves meta-communication. When proposing speculative ideas, clearly label them as such. Quantify probabilities. Explain what observations would falsify the hypothesis. Acknowledge mainstream alternatives. Make it easy for audiences, specialist and public, to understand the epistemic status of claims. Loeb and collaborators sometimes do this, carefully noting that natural explanations are favoured, but the framing in media appearances can be less cautious. The next few months will test the Loeb effect in real time, if 3 Atlas turns out natural, Loeb's critics will say this proves he's too eager to invoke aliens. Defenders will say he advanced testable hypotheses and followed the data wherever it led. If anomalies persist, if the engineered object hypothesis gains support, Loeb will be vindicated, his early speculation seen as prescient. Either way, the episode will inform how future controversial objects are handled. What's certain is that science is a social process. Data don't interpret themselves. Humans choose which observations to make, which models to test, which hypotheses deserve resources. Those choices reflect not just logic and evidence, but also career incentives, disciplinary norms, and the personalities of key actors. 3I-ATLAS, whatever its true nature, has become a lens for viewing how science actually works, with all its messiness, politics, and human drama. That story is worth telling alongside the physics, because understanding how we know is as important as what we know. Part 10. What detection of artificiality would actually mean. Let's imagine, just for a moment, that the impossible happens. Picture the scenario where months from now, after all the data are in, after every natural explanation has been tested and found wanting, the scientific community reaches consensus. 3I-ATLAS is not a comet. It's something else. Something made. What would it take to believe that? The bar must be extraordinarily high because the claim is extraordinary. You'd need multiple independent lines of evidence, each one strong, together overwhelming. Start with sustained non-gravitational acceleration that sublimation models can't explain. Not just small orbital residuals within error bars, but clear, systematic deviations showing the object is accelerating in ways natural outgassing wouldn't produce. The acceleration would need to persist too long. Comets stop outgassing when they move far from the Sun and cool down. If 3I-ATLAS continued showing thrust long after thermal models say volatiles should be dormant, that's suspicious. Or if the thrust turned on and off, discrete burns rather than continuous sublimation, that pattern would demand explanation. Repeatable changes in jet orientation matter too. If the object reoriented its emission axis multiple times, each time in ways uncorrelated with solar heating or rotation, you'd have to ask what's controlling the direction. Natural comets have jets tied to active regions on the nucleus. Those regions stay fixed relative to the surface. As the body rotates, jets sweep around, creating predictable patterns. Arbitrary reorientations unconnected to rotational states suggest external control. Spectral anomalies would be damning. If spectroscopy revealed emission lines from metals, unusual molecular species, or patterns inconsistent with cometary volatiles, that's a red flag. Comets are made of ices and dust, primitive material left over from solar system formation. They shouldn't contain manufactured compounds or processed metals. Detection of such materials would require exotic explanations, with artificiality on the list. Radio or radar signatures could help. An artificial object might emit electromagnetic radiation, either intentionally as a beacon or unintentionally from internal systems. Radio telescopes have listened to various anomalous objects over the years, usually finding nothing. But if 3I-ATLAS emitted narrowband radio signals, modulated in non-natural patterns, that would be extraordinary. Even thermal radio emission with unexpected spectrum could hint at internal heat sources beyond solar warming. Then there's trajectory analysis. Is the orbit special? Does it seem designed? Interstellar objects arrive from random directions with random velocities determined by their galactic journey. But an engineered probe might target the inner solar system deliberately, choosing a trajectory that maximizes observation time or tests specific conditions. Statistical arguments here are weak because we have so few interstellar visitors to compare. But if 3I-ATLAS's path showed features that seemed too convenient, too finely tuned for close solar approach, combined with Earth proximity, suspicion would grow. The combination matters more than any single observation. One anomaly can be explained away. Maybe the acceleration is just asymmetric outgassing we don't fully understand. Maybe the spectral feature is contamination or misidentification. But if you stack up acceleration plus spectral anomalies, plus radio emission plus trajectory fine-tuning, natural explanations become strained. At some point, invoking multiple unlikely coincidences becomes less parsimonious than accepting the simpler hypothesis that the object is artificial. Verification protocols would need to be rigorous. The SETI community has discussed procedures for confirming technosignatures. Independent observatories must replicate findings. Multiple analysis teams should examine the data separately, checking for errors or alternative interpretations. Statistical significance must exceed 5 sigma, the standard for major discoveries in physics. Peer review must be open and adversarial, with skeptics given full access to data and methods. The geopolitical dimension would activate immediately. Who owns the discovery? Which nation or institution gets credit? Does artificial mean current technology or ancient artifact? If it's a probe from an active civilization, are they watching us now? Should we attempt communication? These questions leap beyond science into diplomacy, security, and philosophy. The United Nations has an Office for Outer Space Affairs that theoretically coordinates international responses to such scenarios. But no actual protocol has been tested for an artificial object entering the solar system. Would governments classify information? fearing public panic or wanting military advantage? Or would transparency prevail with data shared openly? The answer might depend on what the object does, whether it seems passive or reactive. Mission concepts to intercept 3I-ATLAS would face brutal constraints. The object is moving fast on a hyperbolic trajectory. After perihelion, it will be racing back out of the solar system at high velocity. Catching it requires a spacecraft capable of enormous delta V, the change in velocity needed to match trajectories. Chemical rockets can't do it with reasonable mass. Nuclear propulsion might work, but isn't flight-ready. Solar or laser sails could build speed over time, but probably not fast enough to catch 3I-ATLAS before it exits the accessible solar system. Loeb has proposed fast flyby concepts, small probes launched on minimum time trajectories to intercept the object, while still within a few astronomical units of the Sun. These wouldn't rendezvous, just zip past at high relative velocity, snapping images and spectra during a brief encounter lasting minutes or seconds. Even that limited mission would require rapid development, launch within months, and significant funding. The probability of approval through normal channels is essentially zero. Alternative approaches involve long baseline observation rather than physical intercept. Continue tracking 3I-ATLAS for years as it recedes, monitoring for any behavior changes, radio emissions or trajectory adjustments. Deploy new assets, perhaps dedicated space telescopes optimized for faint object tracking in the outer solar system. The data might never be definitive, but accumulation of evidence over time could shift probabilities enough to inform future decisions. If artificiality were confirmed, the implications cascade outward in every direction. First, we're not alone. That's been suspected, even assumed by many scientists based on the size and age of the universe, but knowing is different. Proof of extraterrestrial technology would be the most consequential discovery in human history, reshaping philosophy, religion, science, and our sense of cosmic significance. Second, interstellar travel is possible. If someone sent a probe across light years, the engineering challenges we consider nearly insurmountable have been solved. That suggests civilizations can persist long enough to develop such capabilities, a data point in the Drake equation estimating how many technological civilizations exist in the galaxy. It also suggests the galaxy might be full of such probes, a network of exploration left by multiple species. Third, we'd have to reconsider previous anomalies. Was Oumuamua artificial too? Are there other objects in our catalogues that we dismissed as natural but deserve re-examination? How many interstellar visitors have passed through undetected because we weren't looking? The discovery would trigger a flood of retrospective analysis, searching archives for patterns we missed. Fourth, implications for humanity's future. If others have achieved interstellar capability, we might too. The feasibility of star travel becomes less speculative and more engineering challenge. Funding and priority for such projects could shift. Maybe we're seeing the trail markers of older civilizations, and our destiny is to join that community. Or maybe we're seeing the remnants of extinct societies, warnings about the great filter ahead. The null hypothesis remains vastly more probable. 3I-ATLAS is almost certainly a natural comet with unusual but ultimately explicable behavior. The compositional transition model probably explains most or all observations. The engineered object hypothesis will likely fade as more data arrive, joining the long list of initially intriguing anomalies that resolve to mundane explanations. But the exercise of considering what artificial would mean is worthwhile. It clarifies what evidence would be needed, what observations to prioritize, what follow-up makes sense, and it highlights the asymmetry. If natural, we learn interesting comet science and move on. If artificial, everything changes. That asymmetry justifies careful scrutiny, even if the probability is tiny. The timeline is closing. By December 19th, Earth's closest approach, we'll have a much clearer picture. Post-perihelion observations will have tracked the object for weeks under intense solar heating. Spectroscopy will have characterized composition. Astrometry will have measured any non-gravitational forces. The data will converge toward an answer, or leave us with frustrating ambiguity requiring longer-term monitoring. Either way, 3I-ATLAS represents a test case for how we handle anomalous observations of interstellar visitors. The process, the debates, the observational strategies being developed now will apply to future objects. As survey telescopes like Rubin come online, discovering interstellar visitors at higher rates, We'll need protocols for rapid assessment, prioritization, and follow-up. 3I-ATLAS is teaching us how to do that, regardless of its ultimate nature. The possibility space remains open. Natural comet, exotic natural object, or something genuinely artificial. The next few months will narrow that space, excluding options as data accumulate. What remains will be the truth, whatever it turns out to be. And that truth will be a story worth telling, whether it confirms what we thought we knew or shatters it entirely. Part 11. NASA reopens Artemis lander competition. While astronomers debate the nature of objects from other star systems, closer to home, NASA is wrestling with how to return humans to the Moon. The Artemis program, named after Apollo's twin sister in Greek mythology, aims to land astronauts on the lunar surface for the first time since 1972. But the path back to the Moon has been anything but smooth, and recent developments highlight the same tensions between ambition and caution that characterize the 3I-ATLAS investigation. NASA announced in late 2025 that it's reopening competition for the Artemis 3 lunar lander beyond the original single contract award to SpaceX. That award, announced years ago, designated SpaceX's Starship vehicle as the system that would carry astronauts from lunar orbit down to the surface. Starship, an enormous rocket still in development, promises unprecedented capability, but has faced repeated delays, technical challenges, and the inherent uncertainties of cutting-edge engineering. The decision to reopen competition reflects both practical concerns and political pressures. Practically, relying on a single contractor for such a critical mission element carries risk. If Starship development encounters insurmountable problems, the entire Artemis schedule collapses. Having a backup option, a second lander design from a different company, provides insurance. It also fosters competition, theoretically driving innovation and cost control. Politically, spreading contracts across multiple companies keeps more constituencies happy. Blue Origin, Jeff Bezos' space venture, has been vocal about wanting lunar lander work. Traditional aerospace contractors like Lockheed Martin and Northrop Grumman have capabilities and political connections. Opening the competition gives them another chance to bid, to propose alternatives to Starship's radical design. The implications ripple through the space industry. Companies now have incentive to invest in lunar lander concepts, knowing NASA might buy them. Engineers and technicians find employment on multiple programs rather than concentrating in one company. The industrial base for space exploration broadens, building redundancy and resilience. But reopening competition also signals uncertainty about Artemis timelines. The current schedule targets Artemis 3, the first crewed landing for the late 2020s. But delays have been chronic. The Space Launch System rocket, NASA's heavy lift vehicle for Artemis, has run years behind schedule and billions over budget. The Orion crew capsule faced its own development challenges. Spacesuits needed for lunar surface operations aren't ready, and now the lander situation adds another variable. Every delay costs money and political capital. Artemis exists in a competitive funding environment where dollars spent on the Moon are dollars not available for Mars missions, space telescopes, or Earth science. Advocates must continually justify the expense to Congress and the public. High-profile setbacks like Starship test flights that end in spectacular explosions create ammunition for critics who argue the money would be better spent elsewhere. The parallels to 3I-ATLAS are subtler but real. Both situations involve operating under uncertainty with incomplete information and high stakes. NASA must decide how much schedule margin to build in, how much redundancy to pay for, how much risk to accept. Too conservative and the program becomes prohibitively expensive, losing political support. Too aggressive and technical failures undermine credibility. Astronomers face similar trade-offs. Allocate too much telescope time to 3I-ATLAS, and you shortchange other science. But allocate too little, and you might miss the observation that clinches the case. Resources are finite. Choices have consequences. The decision calculus mixes technical assessment with intuition about where the high-value opportunities lie. Public scrutiny affects both endeavours. Artemis is a flagship program, visible to taxpayers who fund it. Any setback becomes a news story, fodder for debates about government spending and NASA's competence. 3I-ATLAS, though less expensive, has captured public imagination through the artificial object speculation. Both face the challenge of maintaining support through inevitable uncertainties and delays. The sociology of large projects also parallels. Artemis involves thousands of people across dozens of institutions, each with their own priorities and constraints. Coordinating that complexity requires leadership, clear communication, and mechanisms for resolving conflicts. Similarly, the global astronomy community must coordinate observations, share data, and negotiate authorship and credit for discoveries. Human factors matter as much as technical ones. There's also the question of legacy. Artemis seeks to establish sustainable lunar presence, not just plant flags and leave as Apollo did. That sustainability requires infrastructure, partnerships, and economic rationales beyond scientific exploration. 3I-ATLAS won't lead to sustainable anything in terms of interstellar missions, but it informs how we think about monitoring the stream of objects passing through our solar system. Both are building blocks for longer-term visions. The Artemis lander competition will unfold over months, with proposals, evaluations, down-selects. Meanwhile, Starship development continues, each test flight refining the design or revealing new challenges. The interplay between competition and primary contractor creates a dynamic where success of either path helps the program, but both paths demand resources and attention. For 3I-ATLAS, the analogous dynamic is observation versus theory. Observers gather data while theorists build models. Each informs the other. Discrepancies between observation and theory drive both to improve. The tension is productive, pushing toward better understanding, but it requires managing egos and giving credit appropriately to both sides. Ultimately, Artemis and 3I-ATLAS investigations both test our ability to execute ambitious plans under uncertainty. They require balancing boldness with prudence, optimism with realism. They demand technical excellence but also political skill, resource management, and resilience when setbacks occur. The outcomes will be shaped not just by engineering and physics, but by the human organizations attempting these challenging endeavors. Whether Artemis succeeds in landing humans on the moon this decade, and whether 3I-ATLAS turns out to be natural or something extraordinary, both stories illustrate how modern science and exploration actually work. Messy, expensive, political, uncertain, but driven by human curiosity and ambition that refuses to accept limits. That shared character connects them across very different scales and disciplines. Part 12. Vera C. Rubin Observatory, First Imagery and the Rapid Survey Revolution. A revolution in how we watch the skies beginning right now, and its implications for finding objects like 3I-ATLAS are staggering. The Vera C. Rubin Observatory, named after the astronomer who provided crucial evidence for dark matter, achieved first light in late 2025. This milestone marks the beginning of the Legacy Survey of Space and Time, an ambitious program that will transform our ability to detect and track transient and moving objects. Rubin's design is purpose-built for wide-field surveying. Its telescope, situated on Cerro Pachon in Chile, has an 8.4-metre primary mirror and an enormous camera with over 3 billion pixels. Together they can image areas of sky the size of 40 full moons in a single exposure. More importantly, Rubin will repeatedly scan the entire visible sky every few nights, creating a time-lapse movie of the universe. That cadence changes everything. Traditional astronomy often revisits the same patch of sky months or years apart. Rubin does it in days. When you compare images taken days apart, anything that moved or changed pops out. Asteroids reveal themselves by shifting position. Supernovae appear as new bright points. Comets, including interstellar ones, show up as fuzzy moving objects distinct from background stars and galaxies. The statistical implications are profound. Right now, we've confirmed only a handful of interstellar objects. 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I-ATLAS in 2025. That's 3 objects over 8 years. The sample is too small to draw conclusions about the population. Are interstellar comets common or rare? What fraction are active? Do they have unusual compositions reflecting different formation environments around other stars? Rubin will answer these questions by discovering interstellar visitors at much higher rates. Projections suggest dozens per year once the survey reaches full operation. That abundance transforms interstellar object science from anecdotal case studies to statistical analysis. You can compare distributions of orbits, compositions, activity levels. Outliers like 3I-ATLAS, if they exist, will become apparent against the background of normal interstellar comets. Early warning is another game changer. 3I-ATLAS was discovered relatively late in its approach, giving limited time for follow-up before perihelion. Future interstellar visitors detected by Rubin will be caught earlier, perhaps years before perihelion, allowing extended monitoring campaigns. Watching how activity evolves over a larger range of heliocentric distances constrains models more tightly than snapshots at just a few epochs. The survey will also create archival data. Every patch of sky gets imaged multiple times across multiple filters over years. That archive can be searched retroactively. When a new interstellar object is discovered, astronomers can look back through the archive to see if it appeared in earlier images before anyone recognized it. Those pre-discovery detections extend the observational baseline, improving orbit determination and activity history. For 3I-ATLAS specifically, Rubin came online too late to catch the inbound approach. But imagine if Rubin had been operating since 2023. The object might have been detected at 5 or 6 astronomical units, visible but faint. Early spectroscopy could have characterized composition before any major activity began. The entire evolution, from dormant to active to jet reversal, would have been documented continuously rather than pieced together from sparse observations. This raises a tantalizing question. How many objects like 3I-ATLAS have passed through the inner solar system undetected? We've only been systematically searching for interstellar visitors for a few years. Before that, any object on a hyperbolic orbit might have been noticed but not recognized as interstellar. Archive searches through older surveys have found candidates, objects whose orbits suggest extrasolar origin, but observations were too limited for confirmation. Rubin changes the detection threshold dramatically. Its sensitivity and cadence mean that fainter, smaller objects become discoverable. The population we sample shifts toward lower masses, potentially revealing a different demographic than the few large interstellar visitors we've found so far. If Loeb-style hypotheses about artificial objects have merit, larger sample sizes will either show patterns supporting that, or reveal that 3I-ATLAS and Oumuamua are rare outliers with natural explanations. The data volume is staggering. Rubin will generate tens of terabytes per night, requiring sophisticated automated pipelines to process images, detect transients, and issue alerts. Machine learning algorithms will classify detections, separating asteroids from comets from supernovae from variable stars. The stream of alerts, potentially millions per night, feeds into follow-up networks where human observers decide what deserves deeper investigation. This automated infrastructure represents modern time-domain astronomy. No single person can look at millions of alerts. Algorithms prioritize based on criteria like novelty, rarity, or match to predicted signatures. Interesting candidates get flagged for human review. Really interesting ones trigger rapid follow-up with specialized instruments. The system acts like a global nervous system for detecting and responding to cosmic transients. False positives are inevitable at such scale. Many alerts will be artifacts, cosmic ray hits on the detector, satellite trails, processing glitches. The challenge is tuning algorithms to maximize true detections while minimizing junk. Too strict and you miss rare events. Too loose and you overwhelm follow-up resources with false alarms. Calibration requires testing on known object populations and continuous refinement as the survey progresses. For interstellar objects, the signature is distinct but subtle. Hyperbolic orbits with high eccentricity separate from bound solar system objects. But measuring orbit requires multiple detections over time. A single detection can't distinguish interstellar from an as-yet poorly determined asteroidal orbit. Automated pipelines must track moving objects across multiple nights, fitting orbits and flagging those with parameters suggesting extrasolar origin. The human element remains crucial. Automated systems can identify candidates, but human judgment decides what's interesting enough to mobilize expensive follow-up resources. Spectroscopy, high-resolution imaging, intensive monitoring campaigns all require human decisions about resource allocation. Rubin amplifies the discovery rate, but the community must scale up its follow-up capacity proportionally. Collaboration becomes more important. No single institution can follow up on all interesting targets. International coordination through networks like the International Astronomical Union's Minor Planet Center helps distribute effort. Observers share data, coordinate to avoid duplication, and collectively build comprehensive data sets on transient events. The comparison to 3I-ATLAS is clear. That object received intensive follow-up because its unusual behaviour warranted it. But such decisions were made ad hoc, based on initial reports and growing excitement. With Rubin discovering many similar objects, the community needs formalised protocols for prioritisation. What triggers intensive monitoring? What criteria distinguish routine interstellar comets from exceptional cases worth major investment? Looking forward, the Rubin era will likely include many 3I-ATLAS-like discoveries. Some will be natural comets with interesting but explicable properties. A few might be genuinely anomalous, challenging our understanding and demanding Loeb-style scrutiny. The key is having systems in place to distinguish them, to allocate attention wisely, and to avoid both missing real anomalies and overhyping routine discoveries. The revolution is not just technical but cultural. Astronomy is shifting from small-team, single-target studies to large-scale surveys and big data. That transition requires new skills, new infrastructure, and new ways of organising collaboration. Rubin is flagship of that transformation, and its success will depend as much on human organisation as on telescope performance. For anyone interested in interstellar visitors, the next decade promises to be extraordinary. The trickle of discoveries will become a flood. We'll learn whether Oumuamua, Borisov and 3I-ATLAS are typical or unusual. We'll constrain formation mechanisms, ejection processes, and galactic population statistics. And maybe, just maybe, we'll find something that doesn't fit any natural model, something that forces us to confront possibilities we've only speculated about. Rubin gives us the tools. What we find is up to the universe. Part 13, JWST finds atmosphere on a lava world. While terrestrial telescopes scan for moving objects in our solar system, the James Webb Space Telescope peers outward, studying planets orbiting other stars. Recent announcements from the JWST team include detection of atmospheric signatures on ultra-hot rocky exoplanets, worlds so close to their stars that their surfaces are molten. These discoveries, though seemingly unrelated to 3I-ATLAS, illustrate capabilities and techniques directly relevant to characterizing interstellar visitors. The specific target, an exoplanet designated in the TOI catalogue or similar, orbits its star so tightly that surface temperatures exceed 2000 degrees Celsius. At such temperatures, rock vaporizes. Silicates and metals that are solid on Earth become atmospheric gases, creating an environment utterly alien. JWST's spectroscopic instruments detected signatures of these vaporized minerals in the planet's atmosphere, confirming theoretical predictions about lava worlds. The technical achievement is remarkable. The planet is hundreds of light years away, a tiny point lost in its star's glare. JWST observes during transits, moments when the planet passes in front of its star from our view. During transit, starlight filters through the planet's atmosphere if one exists. Different molecules absorb different wavelengths, imprinting a spectral signature that JWST's instruments can detect. By comparing in-transit spectra to out-of-transit spectra, astronomers isolate the planet's contribution. This transmission spectroscopy technique is one of JWST's strengths. Its near to mid-infrared sensitivity accesses wavelengths where many molecules have strong absorption features. Water, carbon dioxide, methane, ammonia, even complex organics leave recognizable fingerprints. The precision required to detect these subtle signals demands exquisite stability, calibration, and signal-to-noise, all of which JWST provides. Now consider how similar techniques apply to comets. A comet's coma, the cloud of gas and dust surrounding the nucleus, contains molecules that emit and absorb at infrared wavelengths. Water vapour, the dominant cometary volatile, has strong lines in JWST's range. Carbon dioxide, carbon monoxide, methane, other species, are all accessible. Point JWST at a comet, take a spectrum, and you directly measure composition. For 3I-ATLAS, such observations would be invaluable. Optical spectroscopy has provided some composition clues, but infrared is better for quantifying volatiles. JWST could measure isotopic ratios, the relative abundance of different isotopes of hydrogen, carbon, oxygen. Those ratios reflect formation conditions, encoding information about the temperature and chemistry where the comet's ices condensed billions of years ago in another star system. Comparing 3I-ATLAS's composition to solar system, comets tests whether it formed under similar conditions. If isotopic ratios match, The implication is that comet formation is universal, producing similar outcomes regardless of stellar environment. If ratios differ, that suggests variations in stellar nebula chemistry, teaching us about diversity in planetary system formation across the galaxy. The lava world discovery also demonstrates JWST's sensitivity to unusual chemistry. Vaporized silicates in an atmosphere are exotic by Earth standards, but natural given the extreme conditions. Similarly, if 3I-ATLAS exhibited unusual spectral features, metal lines or unexpected molecules, JWST could characterize them precisely. That precision matters when evaluating artificial object hypotheses. Extraordinary claims require extraordinary evidence, and definitive spectroscopy provides that evidence or rules it out conclusively. Scheduling is the challenge. JWST is the most oversubscribed telescope in history. Demand for observing time exceeds supply by factors of 5 to 10. Getting time for 3I-ATLAS requires convincing a review committee that the science justifies displacing other proposals. For a routine comet, that's a hard sell. For an object with potential technosignature implications, the argument strengthens. Target of opportunity programs exist for urgent, time-critical science. Supernovae, gravitational wave events, newly discovered objects that won't remain observable long. 3I-ATLAS could qualify, especially near perihelion when activity peaks and uniqueness is most apparent. But directors' discretionary time is limited and competitive. Many deserving targets never get observed because there simply aren't enough hours. Another JWST capability relevant here is high spatial resolution. At infrared wavelengths, JWST's angular resolution is excellent, potentially able to resolve structure in 3I-ATLAS's coma at large magnifications. Mapping where different molecules are emitting, whether gas is concentrated near the nucleus or distributed broadly, constrains outgassing mechanisms. Jets would appear as localized emission features, while isotropic outgassing produces smooth radial profiles. The lava world result also highlights JWST's role in astrobiology. Characterizing exoplanet atmospheres is a step toward detecting biosignatures, signs of life like oxygen and methane in disequilibrium ratios. That search parallels the technosignature search, motivating scrutiny of objects like 3I-ATLAS. Both seek evidence of phenomena beyond known abiotic processes, and both require rigorous standards to avoid false positives. Public engagement is another parallel. JWST discoveries, like stunning images of distant galaxies or findings about exoplanet atmospheres, capture public imagination. They justify the telescope's multi-billion-dollar cost, maintaining political support for space science. 3I-ATLAS, through its artificial object speculation, generates similar public interest. Leveraging that interest to support follow-up observations and broader search programs is part of the science communication strategy. Instrumentation advances drive both fields. JWST represents decades of development, pushing technologies for mirrors, detectors, cooling systems, and pointing control. Each innovation enables new science. Similarly, advances in ground-based adaptive optics, spectroscopy, and time domain survey capabilities enable better characterization of transient and moving objects. Investment in one area often spins off to benefit others. The lava world finding also reminds us of nature's creativity. Extreme environments produce exotic phenomena that stretch our theoretical understanding. Molten rock atmospheres, methane lakes on Titan, subsurface oceans on icy moons. Each discovery expands the envelope of known possibilities. 3I-ATLAS, whether natural or artificial, adds to that catalogue. If natural, it teaches about interstellar comet diversity. If artificial, it reveals that technology exists beyond Earth. Either outcome enriches our cosmic perspective. Looking ahead, JWST's mission will span years, potentially decades if the telescope remains healthy. It will characterize hundreds of exoplanets, study thousands of galaxies, observe countless solar system objects. 3I-ATLAS might be one of those targets, or it might fade into obscurity before JWST can observe it. But the capabilities demonstrated on lava worlds and other extreme targets show what's possible when we turn our best instruments toward interesting phenomena. The synergy between exoplanet and solar system science is growing. Techniques developed for one apply to the other. Data from both inform broader questions about planet formation, chemistry, and the potential for life. 3I-ATLAS sits at an intersection of these interests, an interstellar visitor carrying information about its home system while passing through ours. Whether we extract that information depends on resources, priority, and luck, with weather and scheduling. But the tools exist. JWST proved that again with its lava world discovery. Part 14, LIGO and gravitational wave community milestones. While optical and infrared telescopes study light from distant objects, another class of instruments listens to the universe through gravitational waves, the laser interferometer. Gravitational Wave Observatory, along with its international partners Virgo and Cagra, continues its observing runs in 2025, detecting ripples in space-time from colliding black holes and neutron stars hundreds of millions of light-years away. These gravitational wave detections seem far removed from an interstellar comet in our solar system, but the parallels in observational strategy and multi-messenger coordination are striking. LIGO's current observing run, designated O4C, began in mid-2025 after a commissioning period to improve sensitivity. Each upgrade brings the detectors closer to their design goals, able to sense length changes smaller than a proton's width across kilometre-scale arms. That extraordinary sensitivity enables detection of more distant, weaker sources, increasing event rates from 1 per week to multiple per day. When LIGO detects a gravitational wave signal, alerts go out within seconds to telescopes worldwide. Those telescopes slew to search for electromagnetic counterparts, optical or X-ray or radio emissions from the same event. This multi-messenger astronomy, combining gravitational and electromagnetic observations, provides far richer information than either alone. The gravitational wave tells you about masses, spins, and orbital dynamics. Electromagnetic follow-up reveals composition, environment, and mechanisms producing light. The coordination required is intense. LIGO can only localize events to large patches of sky, sometimes hundreds of square degrees. Follow-up telescopes must search that entire region quickly before any transient fades. Survey instruments scan broadly looking for new sources. Once a candidate is found, larger telescopes take detailed spectra and light curves. All of this happens within hours to days, demanding rapid decision-making and international cooperation. This model directly parallels what's needed for interstellar object follow-up. Discovery alerts from surveys like Pan-STARRS or Rubin trigger a cascade of confirmatory observations, orbit determination and characterization. Spectroscopy, photometry, astrometry all must happen quickly before the object fades or moves out of view. Resources are limited. Prioritization is essential. The community has developed protocols, learned from gravitational wave campaigns, about how to coordinate efficiently. One lesson is the value of rapid response infrastructure. Having telescopes on standby, queue scheduled to interrupt for targets of opportunity, enables immediate follow-up. Manual scheduling takes days. Automated triggers reduce that to hours or even minutes. For 3I-ATLAS, such infrastructure meant early spectroscopy, an imaging that might not have happened if observers needed to file proposals and wait for review. Another lesson is data sharing. Gravitational wave events are public immediately. Anyone can access the alert and participate in follow-up. That openness accelerates discovery because more observers means better sky coverage and diverse instrumentation. The model contrasts with older approaches where discoverers might hold data proprietary until publication. Open data policies, now standard in many fields, trace partly to gravitational wave astronomy's success. The statistical approach also parallels. With dozens of gravitational wave detections, astronomers can study populations. What's the distribution of black hole masses? How often do neutron stars merge? Are there gaps or peaks in the mass spectrum? Similarly, with growing numbers of interstellar objects, we'll characterize their population. Are hyperbolic orbits uniform or clustered? Do compositions vary systematically? What fractions show unusual activity? Outliers matter in both fields. Most gravitational wave events fit expectations from binary evolution theory. But a few are strange, asymmetric masses or unexpected spins. Those outliers drive theoretical development, forcing refinement of models. 3I-ATLAS, if it remains anomalous, plays a similar role. Most interstellar comets will be unremarkable. The few that deviate from norms demand explanation. Technology development links the fields. LIGO's vacuum systems, lasers, seismic isolation, and data analysis pipelines represent cutting-edge engineering. Some techniques transfer to other areas. Vibration isolation developed for gravitational wave detectors improves precision instruments generally. Algorithms for detecting weak signals in noise apply to radio astronomy, exoplanet searches. Anywhere signal to noise is marginal. The community building deserves attention too. Gravitational wave astronomy required convincing diverse groups to collaborate, sharing resources and credit. National labs, universities, funding agencies across multiple countries had to align. That collaboration didn't happen spontaneously. It required leadership, clear governance, and incentives structured to reward teamwork over competition. The success provides a model for other big science initiatives. For 3I-ATLAS, no formal collaboration exists comparable to LIGO Virgo. Observers self-organise, coordinating informally through email and telecons. That works for small campaigns, but might not scale as interstellar object science grows. Establishing formal frameworks, data sharing agreements, and authorship protocols could improve efficiency and reduce conflicts. False alarms are another shared challenge. LIGO triggers on events that sometimes turn out to be instrumental glitches or noise fluctuations. Distinguishing real signals from artifacts requires statistical analysis and cross-checks between detectors. Similarly, transient surveys generate false positives from cosmic rays, asteroids, processing errors. Vetting candidates is labour-intensive. Automated filters help but can't eliminate all junk. Human verification remains necessary. Calibration is critical in both domains. LIGO must, LIGO, know its detector response precisely to extract source parameters from gravitational waveforms. Similarly, photometric calibration lets astronomers convert brightness measurements into physical fluxes. Errors in calibration propagate to conclusions about source properties. Maintaining calibration across multiple instruments and epochs requires diligence. Looking forward, next-generation gravitational wave detectors like Cosmic Explorer and Einstein Telescope promise sensitivity gains of an order of magnitude. They'll detect mergers across the observable universe, vastly increasing event rates and enabling precision tests of general relativity. Analogously, next-generation optical surveys and space missions will transform small-body astronomy, detecting interstellar visitors earlier and more completely. The philosophical connection is the quest to observe rare, transient phenomena that reveal fundamental physics or exceptional circumstances. Gravitational waves come from the most extreme environments, black holes and neutron stars where gravity is strongest. Interstellar comets sample conditions in other solar systems, carrying information about processes we can't observe directly. Both push the boundaries of what we can learn about the universe. 3I-ATLAS and gravitational wave events also share the element of surprise. We can predict event rates statistically, but individual occurrences are unpredictable. The surprise drives public engagement. People follow breaking news about newly detected events, curious what each new discovery reveals. That engagement justifies funding, sustains careers, and motivates the next generation of scientists. The intersection of gravitational wave and electromagnetic astronomy exemplifies multi-messenger science's power. Each messenger provides unique information. Together they constrain models far better than either alone. As we develop more messengers, neutrinos, cosmic rays, perhaps others, the network becomes richer. 3I-ATLAS doesn't emit gravitational waves, but the principle of combining diverse observations to build comprehensive understanding applies universally. Part 15. Foremost first light and new spectroscopic capacity. We need to talk about what just happened in the Chilean desert, because while you were sleeping, the rules of the game changed. Mid-October 2025. A new instrument opened its eyes for the first time, and what it sees could reshape how we respond to the next interstellar visitor. The instrument is called Foremost, and if you think that sounds like the name of a corporate conference room reservation system, you're not alone. But don't let the mundane acronym fool you. This thing is a monster. Foremost stands for 4-meter multi-object spectroscopic telescope, and it lives at the European Southern Observatory's Paranal facility in Chile. Picture this. You're standing on a mountain peak in the Atacama Desert, one of the driest places on Earth, where the air is so clear that stars don't twinkle, they just burn. The very large telescope, which already sounds like someone gave up on naming things, is already up there doing its work. Now it has a new companion. MOST doesn't have its own mirror. It piggybacks on one of the VLT's 4 8.2-meter telescopes. But what it brings to the party is something the astronomical community has been craving for years: spectroscopic firepower on an industrial scale. Here's what makes FORMOST different from almost everything else pointed at the sky. Most spectrographs can only look at one object at a time, maybe a handful if you're lucky. FORMOST can capture spectra from 2,400 objects simultaneously. Let me say that again. 2,400 spectra at once. It's like the difference between fishing with a single hook and dragging a net the size of a football field through the ocean. You're going to catch things you weren't even looking for. The instrument works by using something called fiber positioning robots. Imagine 2,400 tiny mechanical arms, each one independently aiming a fiber optic cable at a different star, asteroid, comet, or galaxy in the telescope's field of view. The field of view itself is massive, covering roughly 4 square degrees of sky. For comparison, the full moon is about half a degree across. FORMOST can study an area 16 times larger than that in a single pointing. It splits incoming light into 3 channels: low resolution for fast surveys, medium resolution for detailed work, and high resolution for precision measurements of stellar chemistry. This isn't just a new tool, it's a new category of tool. So what does this mean for small body science, for the comets and asteroids and mysterious visitors that wander through our cosmic neighbourhood? Everything. Because the bottleneck in astronomy has never been finding objects, it's been understanding them. Rubin Observatory, when it comes online, will discover tens of thousands of new moving targets every single night. But discovery without characterization is just a list of coordinates. You need spectra to know what something actually is. What's it made of? Is it rocky or icy? Does it have organic molecules? Is it outgassing? Is it covered in dust or bare rock? Is it an asteroid or a dead comet or something we don't have a name for yet? This is where FORMOST becomes critical. Its ability to simultaneously observe thousands of targets means it can conduct massive surveys of asteroids and comets, building libraries of spectral data that will help us classify objects faster when new ones appear. It can study the background population, the ordinary residents of the solar system, which gives us the baseline we need to recognise when something extraordinary shows up. And because it can observe very faint objects, things that are either small or distant or both, it extends our reach into populations we've barely sampled. Trans-Neptunian objects, centaurs, fragments from recent breakups, all of them become accessible in ways they weren't before. But here's where it gets interesting for our story. Think about what happened with Oumuamua. By the time we realised it was interstellar, it was already leaving. We got a few frantic observations, some low-quality spectra that told us almost nothing about its composition, and then it was gone. By the time Borisov showed up, we were better prepared, but spectroscopic time on major telescopes is expensive and competitive. Every hour spent on a comet is an hour not spent on distant galaxies or exoplanet atmospheres. Observing time is rationed like water in a drought. FORMOST changes that equation. It doesn't eliminate competition for telescope time, but it dramatically increases the spectroscopic bandwidth available to the astronomical community. If an interstellar object appears, if something like 3I-ATLAS gets confirmed and needs immediate follow-up, FORMOST can be part of a coordinated response that doesn't require abandoning other scientific programs. It can take spectra of thousands of comparison objects to establish baselines while other instruments focus on the target itself. It can monitor the object over multiple nights without dominating the schedule. It makes rapid response spectroscopy feasible in a way it simply wasn't before. Imagine if FORMOST had been operational when Oumuamua appeared. We could have obtained detailed spectra across different rotation phases, tracking compositional variations across its surface. We could have monitored it for signs of outgassing or dust production at detection limits far below what was possible. We could have compared its spectrum to thousands of known asteroids and comets simultaneously, looking for matches or anomalies. We might have answers instead of arguments. Now think about 3I-ATLAS. If it turns out to be genuinely interstellar, if those early velocity measurements hold up and it's confirmed as our third visitor, we'll be facing it with a completely different arsenal than we had for the first two. Rubin will likely spot it early and track it precisely. JWST can provide infrared characterization, and FORMOST can deliver spectroscopic data at a volume and cadence that was science fiction 5 years ago. If there are metallic absorption lines suggesting a surface we've never seen before, we'll catch them. If there are emission features indicating unusual chemistry or unexpected volatiles, we'll measure them. If the spectrum changes as the object rotates or as it approaches the Sun, we'll document it. The timing almost feels intentional, doesn't it? 3 potentially interstellar objects in 6 years, and suddenly we're deploying instruments that were designed for different purposes, but turn out to be perfect for studying exactly these kinds of anomalies. Rubin finds them, Foremost characterises them. JWST sees what they're made of. It's like we're assembling a toolkit without quite knowing what we're building it for, and only now as the visitors arrive are we realising what we've created. But here's the uncomfortable question that keeps me up at night. What if 3I-ATLAS is genuinely strange? What if the spectra come back showing something that doesn't match any known composition, or features that vary in ways natural objects shouldn't vary? What if we finally have the instruments to see clearly, and what we see doesn't make sense? Because that's the thing about better tools. They don't just answer questions, they reveal how much we didn't know we didn't know. 3I-ATLAS may be the next big anomaly, or it may be a perfectly ordinary comet that happens to be moving quickly. We don't know yet. But emerging instruments like Rubin, Foremost, JWST and others are reshaping our ability to detect, verify, and possibly challenge our assumptions about what interstellar visitors can be. We're entering an era where we won't have to choose between finding anomalies and understanding them. We'll be able to do both. And that means when the next visitor arrives, and there will be a next one, we'll be ready. The question is, will we like what we find?